We have spent 3 weeks talking about logic. That shows how important logic is and how fundamental logic is to the rest of this class. Next, I will talk about the last part in logic, which is argument with predicates. There will be 2 videos for this part. In this video, I will introduce inference rules for predicate logic. Just like propositional logic, in order to prove an argument to be valid, we need some help from some inference rules. In the second video, I will show you how we can use those inference rules to prove an argument with predicates to be valid. Let's first look at some examples of arguments with predicates. Assume the domain consists of all my CS students. The first example says, all the CS students must take discrete math. Thus, some CS students must take discrete math. You can see this is an argument, especially it's an argument with predicates. We can translate this statement into logical expression. Here it is. The logical expression is, for any x, px implies there exists x, px. Here, px represents x must take discrete math. In general, what this logical expression means is, if every element has property p, then some element has property p. Now think about, is this argument valid? The answer is yes, because we know if all the elements have property p, then of course, some of the elements must have property p as well. Second example, all the CS students must take discrete math, thus Alice must take discrete math, where Alice is a CS student. Same as the first one, we first translate this statement into a logical expression. The logical expression is, for any x, px implies pa, where a is a constant. Why is a constant? Because here Alice is a particular element in the domain. Therefore, when we translate that into a logical expression, we need to use a variable representing a constant to represent it. And in general, this logical expression can mean that if every element has property p, then a particular element has property p. Is this logical expression valid in general? It is valid because, of course, if all the elements in the domain have property p, then any particular element must also have property p. Third example, all the CS students must take 261 and 358. Thus, all CS students must take 261 and all the CS students must take 358. The translation is this logical expression. And this is the general meaning for this logical expression. Is this one valid? It is valid as well. Later on, we are going to see a more formal proof on why this argument is valid. Last example. Some CS students graduate with honors. Thus, all the CS students graduate with honors. The translation is this one. And the general meaning of this logical expression is, if some element has property p, then all the elements have property p. Is this one valid? Some of you may already felt that this one doesn't make any sense because this argument is not valid. So from these 4 simple examples, you can see argument with predicates are still arguments. Therefore, some of them are valid, some of them are not. But how can we prove a given argument with predicates to be valid? First of all the equivalence laws and the inference rules we learned from propositional logic still hold here. However, those laws and inference rules are not enough. Therefore, next, I'm going to introduce 4 more inference rules specifically for predicate logic. Here are the 4 new inference rules: universal instantiation, existential instantiation, universal generalization, and existential generalization. The first rule is any x px can imply pc, where c is a particular element or any arbitrary element in the domain. Here, what this means is if for any x px is true, then pc must be true. This rule is very intuitive because if all the elements in the domain have property p, then of course any element, either it's a particular element or an arbitrary element in the domain, must also have this property. The second rule is some x px can imply pa, where a is a particular element not previously used in the proof sequence. How do we understand this rule? Well, since for some element px is true, that means there must exist some element in the domain which has property p. Therefore, even though we don't know what this element is, we can use notation A to represent this particular element. Later on, I'm going to explain why we cannot use a notation or letter that previously has not been used. Third rule, PC can imply for any x px, where C is an arbitrary element in the domain. How do you understand this rule? What this rule says is if for any arbitrary element in the domain, it has property P, of course you can imply all the elements in the domain have property P. Last rule, PA can imply there exists x px, where A is a particular element. This rule says if a particular element in the domain has property P, then of course you can imply that there exists an element in the domain such that x has property P. Of course, you can do that because you already know the element is A. To summarize, look at those 4 rules. The first 2 rules can basically be used to remove the quantifiers in front of the predicates. And the last 2 rules can be used to add the quantifiers to the front of predicates. Next, let's see the rules one by one. To repeat the first rule, universal instantiation is for any x px can imply pc, where c is a particular element or any arbitrary element in the domain. But note that there's a restriction when you use this rule. The restriction is if c is a variable representing any arbitrary element in the domain, then this particular notation or letter cannot be already in the predicate representation itself. Let me show you what I mean by that. For example, this cannot imply this side. Why is that? Let's use one particular example to show that. For example, if the domain is the integer domain, let's use pxy to denote y is greater than x. Then we know that this one is true, because what this says is for any integer x, there exists an integer y such that y is greater than x. But this one is false because it says there exists an integer y such that y is greater than y. As you can see, if we apply the rule incorrectly by introducing a variable y, which is already in the predicate representation, then we will imply from something true to something false. Now let's see how we can use this rule in a correct way. In the example, we need to prove this argument is valid and the domain consists of all my students. First of all, let's translate this argument. Cx denotes that x is a CS student, s is a constant symbol. Why do we need x? Because in the argument, we have Alice, who is a particular CS student. Therefore, we need to use a constant symbol s to denote Alice. And we use dx to denote x has to take discrete math. Now the translation is this one. How do we prove this argument to be valid? Even though this is the argument with predicates, we can still follow the steps as in propositional logic. If you still remember, step 1, we list both premises. Next, let's use backward thinking because the conclusion is DS. And if you look at these two premises, only the first one has D predicate in it, even though we don't see S in it. But that's where we're going to use universal instantiation. So by that rule, we can imply from step 1, the first premise to this one. Here S is a constant symbol. Now you can see by combining 2 and 3 and the first inference rule from propositional logic, we can conclude DS is true. Second inference rule, for some x px can imply PA, where A is a particular element. And the explanation of this rule is, if P is true for some element of the domain, then we can give that element a specific notation. Of course, this rule also has some restrictions when you use it. The restriction is A must not be used before. Why is that important? Let's see one incorrect use of this rule to understand better. There exists x, pxa cannot imply PAA. Why? For example, if the domain is the integer domain, and we use pxy to denote x is greater than y, and a is equal to 1. Some of you may ask, here is pxa, how can we define pxy? The reason is when you define it, you can use any letter or variable you want. But when you use it, you can substitute the parameters of the predict function using the letters you choose. Okay, now let's see what this logical expression means. It says, there exists an integer x such that x is greater than 1. And we know that can be true. However, this one says 1 is greater than 1. Obviously, that's false. So we can see if we don't follow the restriction on the use of this rule, and we introduce an A, which has been used before, then we would end up with implying from something true to something false. There's another way we may use this rule incorrectly. This is not because of the restriction. Let's see what this incorrect use is. For any x, there exists y, qxy cannot imply for any x, qxa. This is another common mistake people make because people see, well, there is this existential quantifier in front of qxy, and according to the rule, why don't we just instantiate with a letter a? Let me show you next why this is incorrect. For example, again, if the domain is the integer domain, and we use qxy to denote x is greater than y, then this logical expression means that for any integer x, there exists an integer y such that x is greater than y. And we know that is true. But this logical expression means for any integer x, x is greater than a, where a is a constant. Obviously, you cannot find a constant a making this true. So this is false. The problem is when you apply this existential instantiation rule, you have to make sure the existential quantifier is in front of the whole logical expression. Now let's see how we can correctly use this rule. Here is the argument with predicates. Step 1, as always, we list all the premises we can identify. There are only 2 of them. We know the conclusion is QA. But if you look at both of the premises, there's no A in it. So we will have to use the existential instantiation rule. Well, looking at these 2 premises again, you may see the first premise has Q in it. So let's just use the universal instantiation rule to instantiate it. So we have step 3, PA implies QA. Then you can use the existential instantiation rule to imply PA from step 2. And then applying the first inference rule from the propositional logic, combining 3 and 4, you can imply Q of A. So now it seems like you have done the proof. But remember, when we talk about the existential instantiation rule, we said when you introduce a notation to represent a particular element, you have to make sure this notation has not been used before. But now you look at the current proof sequence you use, this A has been used in step 3. So this is not a correct proof. The correct proof should be, we need to apply the existential instantiation rule first. So there exists y, py implies pa, where A is the particular element in the domain. And now we can apply the universal instantiation rule on the step 1, on the first premise. Then we have PA implies QA. Because for that rule, the only constraint is the introduced notation should not have been used in the predicate representation. And finally, now you can combine 3 and 4 and the first inference rule from propositional logic to imply QA is true. This is the correct proof sequence for this example. Third rule, universal generalization. The rule says PC can imply for any x, px, where C is an arbitrary element in the domain. Here's the explanation. If P is true for any arbitrary element in the domain, then of course we can say all the elements in the domain have this property P. And the good thing about this inference rule is there's no restriction. Let's see one example to see how we can apply this rule to prove an argument to be valid. Step 1, we list all the premises, and there are 2 of them. But the conclusion is for any x, qx. We cannot just simply combine step 1 and step 2 and using the first inference rule from proposition logic to come to this conclusion. The reason is there is this universal quantifier outside of this implication. So we want to first remove this quantifier. And if you recall, I said the first 2 inference rules can be used to remove the quantifiers. So we are going to apply the universal instantiation rule to step 1 and to step 2. And combining step 3 and step 4 and the first inference rule from the propositional logic, we can conclude Q of C is true. And now this is where we apply the universal generalization rule to conclude for any x, Qx is true, because C is an arbitrary element in the domain. Last rule, existential generalization. This rule says if PA is true, we can imply there exists x px, where A is a constant element in the domain. The meaning of this rule is if something has been named as having this property P, then we can say there exists some element in the domain that has property P. There is also a restriction on the use of this rule. Because you are introducing a variable x, we have to make sure x has not appeared in the predicate. Why? Let's see an example. Basically, PAY cannot imply there exists y, PYY. The reason is if the domain is integer domain and PXY denotes y is greater than x and A stands for 0, then PAY means y is greater than 0. It does not mean y is greater than y. Let's see how we should use this rule correctly. This is a very simple argument. The premise is the only one. And in order to prove the conclusion, from the previous example, we can see we should first remove the quantifier in front of the predicate. How can we do that? Which rule we should apply? The rule is universal instantiation rule. By using that rule, we can imply PA is true, where A is a particular element. And now, using the rule we just learned, existential generalization, we can imply there exists x, px.